Okay, guys, so this will be now the last video. I'm going to cover now 12.14. I thought in the last video, that was the last video, but apparently we need to cover 12.14, chemical calculations using molar volume. Now, I could solve these problems different ways, and probably some of the problems I want to solve different ways because I think the solution is much easier to get the final answer, not to use molar volume. But again, I'm going to stick to molar volume here. And if I find a solution that is much easier now, there's a much easier way to solve a problem, I'll propose you guys probably a different way to solve this problem, because you can always go to the to this part of the chapter and check this example, the way the book solves this, and if you like it, you can use it. Again, problems could be solved, guys, different ways. It's just a matter of the way you like the problem to be solved. So, all right, just bear with me. So I'm going to start here with example 12. Example 12.21. So let's do example 12.21 here. And so on page 531. And so here's what's given. Fluorine gas, F2, is one of the most reactive of all gases. Calculate the volume in liters of 15 grams of sample of this gas at STP condition. Now here you can definitely use, guys, the molar volume concept. We know that at STP, any gas, any 1 mole of the gas occupies 22.414 liters. So as long as we now convert now this 15.0 grams of the fluorine gas F2, we can just use now this conversion factor to pretty much find out the volume, of this gas now occupying at that certain temperature and pressure. So 1 mole of this will be, so fluorine is 19 times 2, so that will be, looks like 38.00 grams of F2 would be 1 mole. And again, guys, you always should really use the calculator when you're taking the exam so that you don't make any, frivolous mistakes. And I don't want you guys to get penalized for choosing the wrong answer. Okay, so 1 mole now, so you got the moles now, and then you can say that 1 mole of any ideal gas, let's say in this case F2, will be occupying 24.14 liters. Cancel, cancel, and that's how you guys would solve the problem. Now, calculating the volume using the molar volume of the gas. So that will be now 15 divided by 38, and then that would be now multiplied by 22.414. And again, all we do now here is using the molar volume as a conversion factor. And so what I got here, 3 significant figures. Final answer 8.85 liters of F2. This is the unit that stays. Okay, so now, guys, we're going to go into now the next example here. So I'm going to do example 12.22 here now on page 532. All right, so let's get to it. So I'm going to do just one of these problems. If I do one, you guys can do the same way now using the same procedure to solve the other one. What is the mass in grams? So this is what's given now. Volume, 2.50 liters. And you have the temperature here, 28 degrees Celsius. Again, we're going to convert it real quick. Kelvin. And the pressure here, they also give you guys as 1.05 atmospheres. And so the question here, what is the mass in grams? So we need the mass, for example, in grams of carbon monoxide, FCO, question mark. Now, I can definitely solve this problem, different ways. But they want me to use the molar volume here. So what I'm going to find out here using a PV nRT, I'm going to do it, guys, the way I explained you guys before, how I would do now molar volume, because this is supposed to be just the ratio volume of the gas to occupying 1 mole of the gas occupies a certain volume. So it's a ratio of that volume over 1 mole, molar volume. And so this will be now the R times T over the P. So what I'm going to do now is I'm going to find conversion factor, guys, of this ideal gas. And that will pretty much help me solve this problem. Atmosphere liters, mole Kelvin, and now times now the temperature, which is 28 plus 273. That looks like, let's say if it's like 301 looks like. So let me just write down here now 301 Kelvin here. And so the next one will be divided by, of course, now the pressure, which is 1.05 atmospheres. Now, I'm going to cancel the units, guys, I don't need. And as you can see, guys, nicely, I got the correct units, liters per 1 mole of the substance here. That's what the molar volume definition is. So it's going to be 0.08206 multiplied by 301, and then divided by 1.05. And so my now conversion factor here will be definitely mole. That's the unit that stays, 1 mole, and will be at 23.5 liters. So that's my conversion factor. 1 mole of this gas occupies 23.5 liters. And that is pretty much, guys, your what's called molar volume here as a conversion factor. Now, so they want the mass, but they're giving me, guys, the volume. So I'm going to say the mass of the CO2 now is equal to, so I'm going to state what they give me here is 2.50 liters multiplied. And so what I'm going to do next here is, let me just, I have this set up, this pop-up in my computer, where every time I get the message, it just pops up. And so now it's covering my whiteboard here. Little inconvenience here, guys. So let me just manage it. There you go. So let me just get rid of that. All right, give me just, guys, a moment. There you go. So I got rid of it. So some little technical difficulties. Okay. So now if I given, guys, 2.50 liters of the, not CO2, by the way, right? Supposed to be carbon monoxide gas. Let me just erase that 2. It's not supposed to be here. And so what happens here now, can use now, this is a conversion factor. And the way I'm going to do it, guys, is I'm going to say that 1 mole of CO is equivalent to 23.5 liters of CO. So the same units, guys, will, of course, will cancel out. And so once I know the moles of CO, I'm going to say 1 mole of CO is equivalent now to molar mass of it. And the molar mass, guys, molar mass of CO is 12.01 plus 16. So that is 28.01 grams of CO. So this will cancel. All I have to do now just the, just multiplication division here. So let me use my calculator now, do this calculation here. So that's 2.5 multiplied by 28.01 and then divided by 23.5. And that's how, guys, you solve the problems. So it's 3 significant figures, 2.98 grams of CO. Now, this is the way, guys, how you solve the problems using this molar volume as a conversion factor. Of course, you can do it different ways, guys, solving these problems. And honestly, this will not be one of my best way of solving it. I mean, I can do it this way. I can do it different other ways. And again, if you guys have any questions how to do this problems different ways, just ask me, guys, during our live Zoom sessions here. Okay. So now I'm going to go to a different problem here that I can see that they want you guys to use a stoichiometry here. Here, example now, 12.23. You got the following chemical reaction here. Lithium now solid here, plus reacting with the N2 gas. It produces, guys, the 2 lithium nitrides. solid. All right, let's see what's given here. Lithium metal is one of the few substances with which nitrogen gas will react. What volume in liters of N2 at STP? So I'm giving guys the STP. That means that the temperature is 273.15 Kelvin and the pressure is 1 atmosphere right here, right away. I extracted information. So they also giving you guys the mass of the lithium, 75.0 grams of lithium metal. And they want you guys to figure out the volume in liters here. I mean, there are different ways to solve these problems. Question mark. Now liters. So, I mean, this is the STP here, standard temperature pressure. I know that any gas, any ideal gas is that, in other words, the conversion here is 1 mole here, let's say, of gas N2 here will be occupying 20, now 2.414 liters. So I can use this one as the last step in the conversions, guys, to get my liters here. So, but before I do so, I have to get, guys, now the moles of the nitrogen that is reacted here. And so what I'm gonna do here first is, let me see what's given. I got 75 grams of lithium, fine. If I know the lithium here, I can do mole-to-mole ratio here, 6:1 to figure out the now liters. If I have the moles of this, I can get the moles of this. And if I get the moles of N2, I can get now the liters using this conversion factor. So let's do it, guys. So I'm gonna state now that I have 75.0 grams of now of lithium. I'm gonna convert that into the moles. 1 mole of lithium. This is like 6 point something, 6.94 according to your book. So I'm gonna use that number, 6.94 grams of lithium. Canceled. So now I need to get now from lithium to nitrogen reacting. So that will be now 6 moles of lithium, 6 came, guys, from this coefficient mole-to-mole ratio to 1 mole of nitrogen now. And so if I need to now to figure out the liters, I can use this as a conversion factor. I can say now 1 mole of nitrogen is equivalent to 20.414 liters. And that would, guys, solve me the problems. But the problem now using the molar volume as a conversion factor, guys, to calculate the desired quantity of whatever the term, guys, they want me to calculate. In this case was just, the volume here, of course, but based on the mass of other substances, guys, in this chemical reaction. Okay, so let me just do the calculation here. 75 divided by 6.94 divided by 6, and then multiply by 22.414. And so what I got here now is 3 significant figures. I got 40.4 liters of nitrogen gas, guys, will be now consumed here in this reaction to form the product with a certain quantity. So in other words, this whole thing, 75 grams, when you consume now by reacting with now 40.4 liters of nitrogen gas to get whatever the amount, guys, you're trying to get here. And again, we can get the amount of this, how much we produce based on either this or this amount. There's no limiting reactant here because we calculated now we use this to figure out how many liters of nitrogen needed here. So when these two react now based on the amounts we calculate the nitrogen, they will be both consumed pretty much 100%. If this reaction goes, of course, to the 100% formation of the product to get your final product. But again, here the question was, if you have so many grams of lithium, how many liters of this has to be now reacted? And that would be your guys' final answer here. All right, so let's move on now to the next problem here. And the next problem, guys, here on page 534, there will be example now 1224. Let's see what's given. So you have this typical reaction decomposition, guys, in here in the form of heat. Now you apply heat here, you produce KCl solid plus 3 molecules of oxygen. All right, let's see what's given here. How much of potassium chlorate in grams is needed to generate. So they asking you guys, they're giving you here actually volume of 7.50 liters of oxygen. They're giving you guys the pressure here, 1.00 atmospheres. And they're giving you guys a temperature here, 37 degrees Celsius. And again, we're going to convert it really quick to Kelvin here. It's very important, guys, to do so. So this looks like it's going to be 310 Kelvin here. Let me just make sure that's correct. And so the question here is now to figure it out. Now how much of grams of this has to be now used to get now 7.50 liters of oxygen. And again, the intention here, part of this chapter, to use what's called the molar volume here. And it would not be my best approach solving this problem. The way I would solve this problem definitely is a very simple manner. I would just use the PV nRT to find the number of moles now based on the volume, pressure, and temperature of the O2. Once I get number of moles, I will do the mole to mole ratio, get the moles of this, and then using molar mass of potassium chlorate to find the necessary grams to decompose to get the 7.50 liters. So that's the way I would do it. I mean, to me, it's much simple way to handle this problem. However, they do want to use the molar volume in here. And so the way they do it is that they're going to find out V over N in that particular temperature and pressure. So again, we're going to use the PV-nRT. I took this one, brought down, so it's going to be R times T divided by the pressure. So all I have to do now is plug the units now. I mean, plug the numbers instead of the terms in here. So this will be 0.0206 atmospheres, liters, mole, Kelvin times the temperature here is 310 degree Kelvin here. I mean, not degree, 310 Kelvin, it's absolute Kelvin here. And then we will divide it by the pressure, which is 1.00 atmospheres. All right, so let's get now the conversion factor here. Again, I'm going to use my calculator here. 0.08206 times 310, and then divided by 1. So I'm going to report one extra digit here, guys. It's going to be 25 point, definitely 3 significant figures, 4, and then I'm going to do a little 4 in here. I'm going to put, and so atmosphere canceled. I got Kelvin canceled. I got now liters per mole, and that would be my molar volume here. That would be my conversion factor. Okay, so now, what do we do now next with this? So what are we doing now next with this? So we're going to use this one, of course, as a conversion factor here. So let's start with what's given here. Let's start with what's given here. So, see, my family is bothering me with these text messages. So you guys probably hear my computer constantly popping up, distracting me. And no matter how much I tell them not to bother me, it's still happening. So just bear with me, guys. So let's roll. So, okay, so this is what we're going to do now. So we're given, guys, 7.50 liters. That's what's initially given. We can use now our conversion factor as the molar volume here. I can say now 1 mole of the O2 gas is equivalent to 25.4 little 4 now liters of O2 gas canceled. So now I got the moles in here, and now I can do my mole to mole ratio here. I'm going to say now 3 moles of oxygen. This one came from here, and it will be now pretty much you're getting 3 moles of oxygen from decomposing, guys. 2 moles of potassium chlorate canceled. And then the next step, again, the grams, I'm going to say that 1 mole now of KClO3, and the molar mass of the KClO3 is going to be 122.55 grams of KClO3. I'm going to cancel now these units, and I'm going to get now what they ask, the grams of the substance. And again, it could have been solved now a different way. In my opinion, you know, the different way is much easier to handle. The last problem, I'm going to probably solve it a different way from what, you know, the way they solve it. And I'll show you guys how to also handle these problems, doing it a little, you know, handle them a little different way. Times 122.55. So I got here 3 significant figures. So it looks like the grams that will be used here, 24.1 grams of KClO3. and that will be the final answer. Now, I'm going to now do example 12.25. This looks like a really good problem here. Not an easy one, looks like. And I can already see there, again, using this molar volume concept. So you can guys follow this, but I want to solve it now a little easier way, in my opinion, than the way they do it, so that you guys have another option of handling this kind of problems. All right, let's see what's given here. So they're giving you guys this reaction here, N2 gas reacting with the 2O2 gas, producing a 2NO2 gas. Now, so here's what's given. So they want you to find, guys, how many liters of N2 gas. So they want the volume here of NO2 gas. And they're giving guys the pressure of NO2 gas in here, which is 3.00 atmospheres. They're also giving guys the temperature of the NO2 gas, and that will be 55 degrees Celsius. And again, don't forget, you will have to be now converting that into the 273 Kelvin. So we'll get that in a moment. And so now what else they're giving you? It can be produced from. So now they're giving you information on the reactants. So the first reactant will be the volume here is equal to 20.0 liters of N2. And then they're also giving you guys the partial pressure of N2 here is equal to 1.00 atmospheres. And then they're also giving you guys the temperature here of N2, and that will be now 35 degrees Celsius. All right, what else they're giving you? Well, they give you all the information now about this O2 in here. And so this is what giving you guys, this one here. They're giving you the volume of O2, and that will be now 30.0 liters. They're giving you the partial pressure here of O2. That will be 2.00 atmospheres. And they also give you guys the temperature of O2 at 45 degrees Celsius. Now, what's interesting here is that, you know, these temperatures are different reacting in the same vessel. Practically, I don't know what to tell you here. Usually, once you supply the heat for the reaction, you know, these, you know, reactants really should be at the same temperature. Okay, so they want to put some twist in the problem. That's what they did. Now they also did, so now I'll show you guys that the final product is formed at this temperature now. So you got all this bunch of different temperatures. Don't forget you have to convert them into the Kelvin, which we will do in a moment. But here's the question. So what do they want us to find out now? They want us to figure it out now, the volume of this N2, okay, this particular set of conditions. In my opinion, the best way to handle this problem, not actually go into the molar volumes, but find out the number of moles of this, reacting the number of moles of this. And remember, guys, you will have what's called a limiting reactant once you're given the amounts of both reactants. It automatically triggers the limiting reactant problem. Once you know the moles, limiting reactant now, moles producing this product, how many products will be now produced based on limiting reactant, all you have to do now, use the ideal gas law equation and just find the volume, and that's it. You have number of moles, you got the partial pressure of N2, you got the temperature of N2. All you have to do now, plug it in into the PV-nRT and find the volume from it. So that's the way, guys, I'm going to handle this problem. And again, if you have any questions the way they handle the problem in the textbook, you can always ask me, guys, during the live sessions. But I will use this problem in a much simpler way, calculating it, guys. Okay, so the first thing I'm going to calculate the number of moles of N2. And so I'm going to use, again, the PV-nRT. N is equal to nothing else as the PV over RT. So let me do this now. So the P, the partial pressure of N2 is 1.00 atmospheres. Again, I'm collecting everything from here now, times the volume, which is 20.0 liters here. And then I will divide it by 0.08206 atmospheres, liters, mole, Kelvin, and then multiply by the T. It's 35 degrees plus 273. Again, I'm doing everything, guys, you know, kind of fast. And again, you can always ask me the questions if you have any during our live sessions. That will give us 308 Kelvin. So I'm going to get the number of moles in a moment for N. I'm going to do now the same thing for O2. And now I'm going to just plug the data in here using that. So that would be now the P will be 2.00 atmospheres time the V, which is now 30.0 liters I would divide that again by the ideal gas law constant here, atmospheres, liters, mole, Kelvin, and then I will multiply that by now 273 plus 45. I got 318 here. Let me just switch that. Okay, 300 now, 18 Kelvin. And so now I'm going to cancel the units, guys. I don't really need atmosphere, atmosphere. Now liter, liter, Kelvin, Kelvin. And as you can see, guys, I got the correct units here, moles of N2. So let me do this calculation, guys. So I'm going to do now 20 divided by 0.08206. And then I will divide that by 308. Okay, so I will report one more significant digit, guys, because this is an intermediate result, 791, and I'm gonna put a little 3 here that is not significant, but I will carry it, guys, through the entire calculation here. 2 now times 30 is 60, of course, divided by 0.08206, and then divided by 318. So we got now here 2 point, actually, again, 2 significant figures. Looks like it's going to be 3, 0. Let me just make sure. So it's going to be, let me just do this. Let me report one extra digit as I've been always doing it. So that will be 2 point, actually 2, and it will be 9, and there will be a little 9 here, moles now of oxygen. Okay. So now, since I'm reacting the moles of each, that's a limiting reactant problem. I have to figure out how many moles of this will be now formed based on a limiting reactant amount. So let me do it now, guys. So I'm going to now get the moles of the product, the NO2, based on each amounts of the reactants. Let me just cancel this. Okay. So for the first one, it's going to be 0.7913 moles of N2 times mole-to-mole ratio here is 1 mole of N2 produces always 2 moles of NO2, canceled. So this is now number of moles of the product based on one of the reactants. So we'll also have to do, guys, the other one the same way, 0.7913 now times 2, and that would be giving me, guys, in here 1.58. And I'm going to put a little 3 here, moles of this product, NO2. So my next step is calculate now the same product now based on the amount of the other reactant will be 2.299 mole of, now this is for oxygen, and I have to get the mole-to-mole ratio of oxygen now to the other one. 2 moles of oxygen will be to 2 moles of NO2. So this will be canceling here. And so all we got is just 1 in here, and it will be 2.29 little 9 moles of NO2. Now, so limiting reactant obviously is this one here. This is how much you're going to get. So limiting reactant here is based on nitrogen. So this is my limiting reactant. This is my excess reactant. Okay, so this is how much, guys, I can only form based on each amount of each reactant, because it's always based, guys, on the amount of limiting reactant. Okay, so I got now the moles of my NO2 here. These are my moles. So I can use now PV nRT, where N is equal to, again, PV divided by RT. So if I find now the number of moles of this product form, I can find now through PV nRT the volume that will be produced here as NO2. All right, so let's plug everything in. So the pressure here, of course, is 3. Oh, hold on a second. I think I jumped a little. Hold on a second. I got my number of moles here, so I just have to get the volume here. I just, for some reason, I rushed through this one real quick. All right, so we can pretty much solve now this problem by just, again, using the PV nRT. Let me do it. Let me state it again. PV nRT. And so we do have the partial pressure of NO2. We have the number of moles of NO2 from here. There you go. R is always the same. And we also have, guys, the temperature here, which is nothing else as 273 plus 55. So we got 328 now Kelvin for the temperature of NO2. So again, we got this, we got this, we got this, we got this. All we need to figure it out is the unknown VNO2, and we solve the problem. So VNO2 is equal to now the N times the R times the T divided by P. So I'm going to use now all of this information to solve this problem. I will not have, space here. So what I'm going to do is I'm going to plug everything here, guys. So the number of moles again will be now this number of moles based on limiting reactant, 583 moles of NO2. Now times the R, which is 0.08206 atmospheres, liters, mole, Kelvin. And then I'm going to time it now, the temperature now of this NO2, which is 328 Kelvin. And we'll divide now by the partial pressure, which is given to me, guys, in here, which is 3.00 atmospheres. Okay, so I'm going to cancel now the units I don't need, the mole, the atmosphere, the Kelvin, the Kelvin. I'm going to get, guys, now the liters. And that would be now the solution for this problem. And no other way than, they solved it here in this problem. So let's see if we get, guys, the same answer. 583 now times 0.08206 now times 328 and then divided by 3. So the answer I get, guys, here, 3 significant figures. I got now 14.2 liters of NO2 produced, guys, based on this reaction. Again, this one is a pretty intense problem, in my opinion. And so I got 14.2 liters doing a different way, and that's what they got also, 14.2, guys. If you like the way they did it, please use their way. If you like the way I did it, please use my way. It doesn't matter, again, which way you use, as long as you get the right answer. So this is, guys, was the presentation, the last topic now presented in this chapter and the entire course now. I'm going to pause this last video. Please study hard. We almost finished with the course. And again, I'll see you guys during our live Zoom lecture so that you can ask me, guys, questions.